Good morning. Let's go ahead and get started. We're going to start off Physics 4C, taking a look at light and some of the basic properties. So this chapter, chapter 32, our first chapter for the course, we're going to be looking at specifically reflection and refraction of light. So let's take a look and see what that's referring to. Now, in each of these chapters, what we'll do is we'll have a set of slides that we'll be going through. The slides are based on some slides provided along with the textbook. Now, I've gone in and made quite a few modifications, so this is going to become kind of a bridge for us. It's going to, when you're reading through the textbook, you'll see many of the items that we have listed here are similar to what's in the textbook, and then I'll put additional information in that I hope will make it more clear. Clarifications. So each one of these slide sets is going to start off with a set of topics, and I'm not necessarily going to take a look at all of that right now. I'm going to move ahead to this first slide that's looking at what we call the geometric model of light, or the ray model of light. Light, in many applications, can be thought of as just traveling in a straight line. In fact, it's very likely that you're used to thinking of light as only traveling in straight lines, and so that's what we're going to start off with. So this is considered kind of classical optics, and we can use geometry. We can draw out these paths of light, all the possible paths the light could be taking, and explain how reflection and refraction properties take place. So anyway, this is here's a pencil, and the pencil's in a room where there's some light, and the light is reflecting off the pencil. And what we know is, when an object's being illuminated, we can use our eyes to see light coming from all different aspects of that object. And so the light is striking the object. What this picture shows, it doesn't show the light coming in, it just shows the paths of the light after the light has reflected off of the pencil. And this is showing that it's reflecting off in many different directions. Now I put a little note here. This is geometric optics versus quantum optics, which we'll be looking at in a couple chapters. So light, we now understand, consists of particles. We call these particles photons. And in many situations, we can treat these photons as if they're just traveling in straight lines. But we'll see that there's actually some more complicated or complex or interesting properties that we'll run into in a couple of chapters. All right, so for reflection, we're going to say here is a surface. If the surface is really smooth, then as the path of the light comes in towards the surface and reflects off the surface, it turns out that the angle at which it comes in at is equal to the angle at which it exits. We say that the angle of incidence matches the angle of reflection. And so you can see in these diagrams that's the way this is drawn. Now in classical optics, we just think of this as a straight line path. What we'll find when we get into quantum optics is that there's actually many different paths that the light could be taking, and when all of the effects of all of those possible paths are combined, what we observe is that the light's following what looks like, or is, for practical purposes, a straight path in many situations. And so another item we want to be clear about with the diagrams we have here. When we have a surface, think back to your other physics classes, Physics 4B in particular, or your math classes in calculus. When we define how a surface is oriented, what we do is we use a normal vector. So we use a vector that's actually perpendicular to the surface to define its direction. Now, kind of following that idea, what we do is we measure these angles of incidence and reflection compared with a normal to the surface. So often in our diagrams, when we have a surface, what we'll do is we'll draw a normal just to orient ourselves. And then the paths the light's taking, if you look at these angles, theta I and theta R over here, same thing in the diagram on this side, those are officially what we designate as the angle. So a 0-degree angle means that the light strikes directly into the surface and then reflects directly back out. That would be at 0 degrees. Now what this picture is showing is that when light strikes a surface, like that first picture we had with the light coming off the pencil, in most cases we can see the light coming off in all different directions. Now we can take a closer look at these objects and realize that when we get down to fine detail, that the objects have a rough surface. There's not one particular orientation for the surface. And so what's happening is, even though the light paths, if you follow the light paths coming in here, they're all parallel, when they strike the surface, they get reflected off in different directions. And that creates the effect that we can see objects from many different directions. The light coming off is not just coming off all in one direction. This slide's it's just the same picture over again with a little more information. So they're calling this diffuse reflection in this example where it's coming off in many directions. And they're comparing that with specular reflection, and I'm going to say that, that vocabulary you don't have to necessarily be familiar with. But when we have a smooth surface like a mirror, that's kind of where we're headed here. When we have a smooth surface like a mirror, then all parts of the surface are parallel to each other. When the light comes in and reflects, if it's all coming in together, it all reflects at that same angle together. So just getting some familiarity with how reflection takes place. Now in this diagram, what they've given us, they're saying here is a mirrored surface here, here is a mirrored surface here. And I've got light coming in here at 15 degrees. Now they didn't use the official definition. It should really be listed as, what's the complement here? 75 degrees, I guess. We should be drawing a normal and then drawing the angle. Now they've done this in picture B here. So what they've done is, it's coming in at 15, but what we want to do is say theta 1 then is 75 degrees. So we'll use 75 degrees as the angle of incidence, and then it will reflect, since we have a very smooth surface, it's also going to be reflecting at that very same 75 degrees. Now we can use a little geometry. Since this angle is 90 degrees here, we can draw these normals to the surface. When we draw all that, it becomes kind of rectangular, and so we can say theta 3 is the complement of theta 2 in this particular example. And so if this is 75 degrees, then theta 3 looks like it's going to be 15. And since we've got a second smooth surface, that vertical one, theta 4 is going to be equal to theta 3. Okay. So this would be at 75, 75, 15, and 15. Now if we follow the geometry here, what we find is that the path exiting is parallel to the path coming in. Now that happened because of the 90-degree angle here. So in general, you don't necessarily always get both the exiting path coming parallel to the original path. But these are the sorts of diagrams that you're going to get a chance to go in and work through in the homework problems and in the examples we do here in lecture. So there's a good chance to brush up on your geometry, working some of the problems that we have here. So anyway, this is a little more detail here. So what I've done is I've gone in and defined these different angles. Now they had defined, I think I changed the definitions. I apologize for that. I'm just realizing this right now. What they had as thetas, I switched those to alphas. I thought it was the other way around. So it turns out theta 1 is 15, theta 2 would be the same. If I do this in terms of the alphas, then it's 75 and 75, and the alphas 3 and 4. So again, just, doing some geometric problems. Now, what I'm going to highly recommend is that what you want to do is you want to get a ruler. You want to get a plastic ruler, preferably something that's clear. something between 8 and 12 inches or something in size, and go back and practice doing these diagrams carefully. Because as you know from in your math classes when you're doing geometry, and in physics too, setting up these diagrams, it's easy to confuse yourself if the drawings aren't done carefully. So there are a number of diagrams here that you're going to need to be able to draw pretty carefully to show how your derivations are working. So that's something to watch for. All right, now with mirrors, I'm guessing all of you have plenty of experience looking in the mirror, right, and kind of having an idea of what it looks like when you're looking in a mirror. So what they've done is they've, in the diagram here, we have a plane mirror. And so the plane mirror is turned, sideways to our view here. And so what we're doing is we've got this person here. I know they always have these scary big eyes in these diagrams. Anyway, here's a person with their eye. And what's happening here is that they're looking in the mirror, and the light coming off of this bottle, I guess it's a bottle, some of the light is striking the mirror and coming back towards this person. Now, of course, the light from this object is going off in all different directions. So this diagram just happens to be capturing or utilizing a couple of those paths to see what's going on. And so what's happening here is we've got light from this bottle reflecting back. I'm going to say, I tend not to draw these diagrams with the person's eyes so much, I guess. I guess you can do this either way. But what's happening here is because we're getting this reflection at the same angle as the incident light, if you do a little geometry here, what you can see is that for a plane mirror, the path that the light takes after striking the mirror is going to look as if it's coming from this location. So if you play around with a mirror, if you stand in front of the mirror, and maybe you can say your homework, for after today's class is to look at things in mirrors, spend some time looking at mirrors and playing around with this. But when you hold objects next to mirrors, if you bring the object closer to the mirror, the image from the other side approaches the mirror from the other direction. And that's what we're seeing here. Now, in these diagrams, so we're developing these diagrams, one step at a time here. What we have are what are called objects, and we say that there is an object distance. And the object distance is the distance between the plane where the mirror is located back to where the object is located. Now, what we also have in this diagram is we have the path that the light is taking after the reflection has occurred. Now, that light corresponds to an image. So one way to think about this is that the mirror redirects the light. So the light coming in is spreading away from the object. After striking the mirror, the light is continuing to spread away from the mirror, but it's headed in a new direction. It's been redirected. And what happens when we come off a mirror is that the pattern of the light coming off looks as if it's coming from a different location. And that different location we refer to as the image. And so we have an object distance on the left. We have an image distance on the right. And so we've written that as d sub I. So when we look at the light, it looks as if the light's coming from something back behind the mirror. Okay, so that's how reflection works. Now this is referred to as a virtual image. Let me go back and look at this. This image isn't really, the light never reaches that point. So if you think of what the light actually does is this. The light actually goes this direction and then it goes back this way. So the light is incident on the mirror and then it goes opposite direction. It never goes back behind the mirror. And so an image that appears to be back behind the mirror is considered not to be real. It's called virtual. So, for example, if I put a screen right here, I wouldn't be able to see that image. That image is not going over there. If if in your apartment, let's say your apartment, you've got a bathroom, there's a bathroom mirror inside your bathroom, and on the other side of the wall is someone else's apartment. That means that when you look in the mirror, your image is over in someone else's apartment. Now, you might think, well, I got to go over and apologize that whenever I'm using the mirror, my image is over in my neighbor's apartment. Say, I'm sorry about that, but that's where the mirror is located. You actually don't have to go and apologize because the image being formed is a virtual image. It's not a real image. If it were a real image, then you might think about going over and apologizing. But for virtual images, you don't need to do that. The light doesn't actually reach that location. Okay, so what they're saying in this next slide, they're just pointing out that we have these definitions of real and virtual. And that's going to come up from time to time. Okay, now I think the other thing they point out here is that for a plane mirror, the image distance and the object distances equal each other. They actually are equal to each other. Now, strictly speaking, when we start doing some mathematical calculations here, we say that for a real object, the distance is a positive value, but since that image is virtual, we put a minus sign on virtual distances. So that image distance actually needs to get a minus sign when we start doing the math. We'll see this when we get to more formulas. All right, here's another example of what you can try. Here's a person, they are 1.60 meters tall. That 1.6 meters breaks down into 1.50 meters from the bottom of the person's feet up to where their eye is, and then they have 10 centimeters above where the eye is. And what we're trying to do is place a mirror on the wall or whatever, so that the person can stand there with their briefcase, I guess. I don't know why they have their briefcase. But they're standing there with the briefcase, and they're looking at the mirror. We want the mirror to be able to show the entire person, or I guess really what we're saying here is we want the person to be able to see themselves from top of the head down to bottom of the feet. How big would the mirror have to be? How would it have to be placed? Now, using, again, some geometry here, what we would need is we'd need something so that the light coming from the very lowest part of this person, point A, strikes a mirror and then reflects up to the person's eye. Now, that's going to enable the person to be able to look at the mirror and see their toe. Now, notice, when you try this at home, notice that what the person is doing is they're standing straight up, right? They're not bending over looking into the mirror. So they're standing up. If the person is entirely in a plane that's parallel to the plane of the mirror, then what would happen here is that this distance B needs to be midway between the elevations of point A and point E. So it looks like 75 centimeters. We would need the mirror to start at the 75 centimeter level. Now, in order to see the top of the person's head, in order for the person to see her head, we can follow this light down. Again, we're going to use the idea that the angle of incidence matches the angle of reflection. So the light coming off of point G reflects off the mirror at point F, comes back to the person's eye. That says that for the person to be able to see the top of their head, we're going to need the mirror to be within 5 centimeters of the top of the person's head. So that says 75 centimeters here, 5 centimeters here. It sounds like the mirror needs to be 80 centimeters, or half the height of the person. I got a diagram to follow this up with so we can see some more of the numbers. But that's kind of interesting. Now, the other thing that's interesting here is this diagram, this geometric diagram we drew, is independent, what we've just talked about, of the distance between A and D, which says that if I can get a mirror set up where it starts at 75 centimeters from the ground and it goes up 60 centimeters, this person is going to be able to see their entire self from bottom of feet to top of head no matter how far they stand from the mirror, or no matter how close they come. That's kind of an interesting effect. Try that. If you've got a mirror at home that you can stand in front of, remember you got to stay vertically here. Step closer and then step farther away. What you'll find is you can see the same portion of your body. Standing closer or standing farther away doesn't make a difference. Now, what you can do is you can kind of lean over into the mirror area, and that would enable you to see different parts of, maybe your feet that you couldn't see before. But as far as, standing vertically and doing this, walking closer to the mirror, walking farther back, it won't make that difference. You'll still be able to see the same portion. So let's see what that other diagram, the follow-up one here says. There it is. So just the stuff we had talked about. Oh my gosh, and I got this one. Okay, I changed some numbers here too. Not off to a good start, but I think we're okay with this. It looks like what I did was I used a different person. I used someone who was 150 centimeters tall. And so the 140 got divided into 70 and 70. And the 10 centimeters got divided into 5 and 5. So again, the numbers don't quite match up, but the diagram itself does. And again, one of the key features here is that this effect does not depend on the distance from the mirror. So we're able to get it, once we get that mirror placed so that the person can see from their foot to the top of their head, they can see that from any distance. All right, here is a photo. Now there's a lot of writing here, and I apologize for that. I went ahead again and left a lot of what the publishers had put together for their slides. But what it comes down to is we're taking a look at this picture, and what we're noticing is that, well, here's the sun in the sky, and here's the surface of a lake. And we can see a nice reflection. So you can see the tree here, and here is the reflection of the tree. Here is the sun, and here's the sun. Now, what they're pointing out is that here, the sunlight is coming, or the image of the sun is showing up below the tree, whereas in this apparently reflected portion, the sun shining through the branches. And they're asking, is this picture right side up, or is it upside down? So what they're suggesting is this. Does that picture make more sense? Or does this picture make more sense? I flipped the whole thing upside down. So here, the light's coming through the tree, but the reflected version, the sun is visible. It's not being covered up by the tree. So, which is it? And, I took a look at this. I kind of flipped back and forth between the two, trying to decide. I finally settled on this. I decided that, well, here's probably what's happening. Here is sunlight. Now the sun is so far away that the paths that the light is following coming in from the sun could be thought of as just being parallel to each other. So there's going to be sunlight coming through the tree, and there's going to be other sunlight coming below the tree. Now if I follow that up to the water in the lake, and I just made up a number. I said, let's just imagine that this is at 10 degrees. Well, if it's coming at 10 degrees compared with the horizon, then it would reflect at 10 degrees. So this diagram, thinking about it, kind of staring at it for a while, made me think, oh yeah, there's an example of where the direct path of the sun would come through the trees, but a reflected path from the sun would miss the branches. Now what we also need to do and include in this is actually a reflection of the tree also. So we would need to follow the light from the tree. But when we do that, we find out that this diagram is consistent with the original picture being upside down. So let me show that one more time here, side by side. So this which of these is right side up and which of these is upside down? And so with that diagram we had before, this would be the right side up picture, where the light is coming through the trees and reflecting off of the lake. And then over here, this is, well, that picture was upside down. So the original picture that we started with looks like it was upside down. So I think the arrows, is it this way or is it this way? And I think we've got, this is now with the picture right side up. And this is the picture that was upside down. Okay, using that diagram before. All right, now what we want to do is start getting more into these geometric drawings and practicing how we can follow the different paths of light coming off of a mirror. Now, what we're going to start looking at are mirrors that are not flat. The flat mirrors are definitely the easiest ones to look at, which means they're never going to show up in our homework. Well, I'm not going to say never, but for the most part, most of the examples we're going to be looking at are mirrors that are actually curved. Now, these are referred to as spherical mirrors, and that's because when we curve the mirrors, it's very common to take the mirrors and form the mirrors as a portion of a spherical surface. Now, even if they're not perfectly curved like a sphere, over short distances, short angular distances, we can treat it as if. So any type of curvature, think of your math classes, I guess, and how for any function at a particular location, you can define a radius of curvature for that portion of the function. So that's what we're going to work from, is that approach. Now we've got two different types of curved surfaces, and I'm going to start with surface B over here. This is usually the easier one to think in terms of, so I'm going to start with the one on the right. So let's say that we've got some distant object, and we're seeing light come off of that object, and the light is coming in parallel. The object is far enough away that we can treat it as coming in parallel. Well, here's light coming in. Because of the curve of this surface, what happens is the light reflects, and it reflects in a way where coming off the surface, the light is being brought together. The different paths of light coming in are being bent or reflected in a way where they're coming together. Now, I'm going to call that a converging mirror. So the effect of the mirror is to take parallel light, and after the reflection has taken place, that light will be converging or come together to a point. Now, the textbook doesn't start using the word converging until next chapter, where we start talking about lenses. But converging definitely applies to this sort of mirror. So for a mirror, if I have a concave geometry, now concave means that when I look at the curvature, the light coming in as if it's going into a cave. So that's a way to keep track of concave. The opposite to that is convex. So convex means that the curvature is working the other way, where the mirror surface bulges. So this is bulging in a way where when the light comes in, instead of the light coming off converging, like it did on the diagram on the right, now it's diverging. So I'm going to emphasize this idea of converging and diverging mirrors, because we're going to start using that all the time to talk about lenses, and it's a property that also applies to the mirrors. So I want to get that classification set up where it's reinforcing that idea. And for mirrors, a convex surface, so something that bulges outwards, is called convex, and that leads to a diverging effect for the reflected light. Concave leads to a converging effect. So those are the two different geometries we're going to be working from. Now here's a picture of some object that's far enough out in the distance. So here's a tree, and I'm looking at a leaf on a tree. If I look at the light as it comes off of that, it's spreading out. That's what is always going to happen with all of our objects. once I am far enough away, let's say that that tree is way off in the distance and I've got a mirror here. Here are a couple of those paths of light and they reflect. Now this is a converging surface, it's concave, and so it's going to come to a point here. And that's the idea of distant objects. We can treat their light paths as if they're parallel for the incoming light. Now here's a more detailed look at that. So I've got many, many paths now that they're showing in the diagram coming off a converging mirror. It's concave, so it's going to have converging properties to it. Now what this is showing, unfortunately, is that when you have a spherical surface, not all of the paths of light are going to come together at one point. And so this creates what we call an aberration. It's called spherical aberration. It says that mirrors, a spherical mirror is not going to be perfectly sharp. Now, when I look at different mirrors, spherical mirrors or plane mirrors, the images look pretty good to me. And so what happens is, what we do is we limit the curvature of the mirror so that the curvature is only over several degrees. You know, if I allow this mirror to go maybe 5 or 10 degrees in each direction, all these points line up so well that we really don't notice the aberration that's taking place. Okay, so you know, they kind of warned us that that's something we're going to have to watch for with mirrors in some situations. Now, using this geometry, we find that, using the picture that we had before, let's go back and take a look at it. Let's go back and take a look. What we say is that here is, boy, maybe there's a better picture here too. Yeah, kind of. Let's go from here. We'll have some better examples that come up. For this mirror, the center of its curvature is out here somewhere. If I think of that spherical curved surface, its center is going to be out here. Now, the point where all this light is coming together is referred to as a focal point. The distance from the mirror back to where the light converges is called a focal length. And the focal length we find using we can measure this in the lab, or we can use some geometry and some trigonometry to show that the focal lengths are going to be 1/2 the radius of curvature for the mirror. So that's how the focal length and the radius of curvature are related by that factor of 1/2. Now, it mentions in this slide here that telescopes, where we want to get really, really sharp images, we actually don't use a spherical shape for the mirrors. We use a parabolic shape. Now that's fine for telescopes, because telescopes are always looking at objects that are very, very far away, and the light that's coming in is parallel. It turns out that what we want to use these mirrors for, the objects may not always be that far away. And so we do want to use spherical curvature for our mirrors, and we're just going to realize it's not going to be perfectly sharp, but it's going to work pretty well. So here's the aberration that we get when all the light doesn't come to the same point. But what we're going to find with the lenses, or with the mirrors that we're looking at, is we're going to keep this angular size small enough that all of these reflected points come back to one location. So that's referred to as the focal point, and we've labeled that as capital F. Now let's think about the other important point geometrically, and that's the center of curvature for the spherical surface. So this is the center of curvature for that portion, well, that mirror that we've got. So the mirror is not an enclosed sphere, it's just a portion of spherical surface with C, point C, as the center of that curvature. So what we find is, when we go through and do some geometry here, is that in the small angle approximation, what we find is that the focal length is equal to 1/2 the radius of curvature. So let's go back and see where those are. So the focal length takes us from the center of the mirror, the center point of the mirror itself, out to where the light is coming together, and the radius takes us from the center of the mirror itself out to the center of curvature for the mirror. So that's the diagram, and that what we find is that the focal length f is 1/2 of that radius. Okay, now we can use that geometry that we just saw on the previous page to come up with some ray diagrams for mirrors. So let's see what a ray diagram consists of. What we're going to do is we're going to pick different possible paths that the light could be taking. So what we'll do is we'll start with path 1. Now we're going to call that ray 1. And for the object, that O corresponds to object. And they've got a little arrow situated there. I use little triangles you'll see in my diagrams. But they've got an arrow right there. And what they're saying is light originating from the tip of the object is going out in all different directions. One of those paths would be something that's parallel to this axis of the mirror. Now if I'm coming in parallel and strike this mirror, the return light is going to go right through the focal point. That's what we just saw in terms of what the focal point means for a curved mirror. So that light's going to come out, it's going to go back through the focal point and then continue on. That's path number 1. Now a second path that we could use is we could say, all right, there's also going to be light going through the focal point as it's approaching the mirror. So if it goes through the focal point on the way in, then going back to that diagram we had, it's going to reflect and come out parallel. So that's kind of the reverse of path 1. Path 1 was coming in parallel, back through the focal point. Path 2 is through the focal point on the way in, and then after reflection coming out parallel. Now what I've already got, even after just drawing 2 possible paths, is I now know where the image will form. The image is going to form at the location where those 2 paths intersect. So I can look at where those 2 lines have intersected and say that's where the image will be. Now, we're going to draw a third line just to double check and see if it agrees with what we found. So a third path that we could choose would be this. What we could do is take, again, that same starting point, the tip of the arrow, and what we're going to do is we're going to draw a path that lines right up with the center of the curvature of the mirror. So if I have a path that lines right up with the curvature, the center of curvature, that means when it strikes the mirror, it's going to strike it at 0 degrees. It's going to be a direct hit, and that means the light will get reflected straight back. And so the return light then goes right back through the point O, through the center, and when we draw that third line in, we see that it intersects with the other 2 lines. And what that's telling us then is, yeah, we very, very likely have correctly done this ray diagram. So these are referred to as ray diagrams. Each path we pick is a ray. We had ray 1, ray 2, ray 3, and all 3 of them on the way out are crossing through the same point. And that means that that's going to be the location of the image. Now what we can do is go back to our object, and if we picked different points along the object and drew all these diagrams again, what we would find is that we would be recreating, for every point on the object, that light is going to form an image that correlates with that particular point on the object. So that says all we really have to do is pick one point on our object, carry out these 2 or 3 different lines, find out where they intersect, and we'll know where the image has to be located. So it turns out that the image that we end up with here, it's some of the properties here, it's inverted, it's upside down, unlike that bathroom mirror that we just looked at, right? In this case, the image is real. The light really does come to that location, and we're going to get an image at that particular location. All right, and that's what this slide's saying too, is that the intersection of the 3 rays is going to give us the position of the image for that particular point. Yes, so just kind of repeating what we have already gone over. So we can come up with a formula to represent all of these measurements. It turns out, we're not going to go through all the derivation here, but if we go back to that picture we just looked at, we have an object at a particular point, we have an image that's being formed, we have a focal length from the mirror itself out to where the focal point is located, that's a focal length, and then an object distance measured out to where the object is, and an image distance measured out to where the image is located. What it turns out we can do is we can derive the formula that we've got circled in the yellow box over here that relates to focal length, an object, and image distances. And it's not too difficult, so it's not such a terrifying formula. A couple things to be aware of. The formula itself is pretty straightforward, but focal lengths can be positive or negative, depending on whether we have a converging or diverging mirror. Object distances can be positive or negative, depending if the object is real or virtual. And image distances can also be positive or negative. We mentioned that, depending on if it's real or virtual. So this is, kind of the simplest case. The curvature we have here is what we consider positive curvature. It's converging. So the focal length value would be a positive number. The object is real. The object really does come from that location. And so that would be a positive number. And the image distance in this case also would be a positive number. So in this case, all 3 of these variables are positive. So the formulas are pretty easy, but you do have to keep track of signs, plus or minus, on each one of the values. Now, one of the things also that you have to be careful with on this formula is it's a bunch of inverses. Now, we've already seen this in Physics 4b. We saw this when we were adding resistance in parallel or capacitance in series. So you've seen formulas like this, and maybe you found out that you have to step through the problems a little carefully to make sure that you remember to invert the results. Once you've solved the right side of that equation, you've got to do an extra inversion to solve for the focal length. But that's kind of what we're looking at. Now, along with the focal length formula, we also have what we call a lateral magnification. And so magnification is defined this way. It's HI over HO, H of the image over H of the object. And if we go back and take a look at our diagram, here is the height of the object. Notice how that's measured perpendicular to the mirror axis. And so we sometimes refer to that as lateral magnification. And the HI also measured perpendicular to the axis. So in this case, we have a magnification greater than 1. We can see that the image height is greater than the object height. Now, what we can also see from this diagram, this is a nice diagram, we have 2 angles here which match each other. The path that we have here is one that goes right towards the center of the mirror itself and then reflects back at a matching angle. And that says that when we look at this diagram, we've got a couple of similar triangles, and they're right triangles. There is a right angle here. There is an angle theta here, and that's for the triangle O prime A. And then we have another triangle, which is I prime A. And those two triangles are similar, which means we can set ratios of sides to each other. So that says in our magnification formula, what we can do is say, hey, this is what we want magnification to tell us. How big is the image compared with the size of the object? Well, that ratio is going to be the same thing as the ratio of the image and the object distances. So that gives us two different ways that we can think about how to determine magnifications, or how the magnifications are going to be related. Now this part of the formula has a minus sign in it. It's got a minus sign there. And that has to do with the way we've defined positives and negatives. Let's go back and look at that diagram before one more time. We had said that in this diagram, the DOs and the DIs are both positive. But the HOs and the HIs are opposite. So, one of those is going to be positive and one's going to be negative. Kind of like conventionally, what we do is say that the object here is positive. It's a positive height. And so the image then we would assign to have a negative value. So, and that's why in this particular example, so if it was the example we looked at, that would be a negative value, that would be positive. So the magnification would be negative, and a negative magnification tells us there is an inversion that has taken place. Now the DIs and DOs are both positive, so there is actually an explicit negative sign in that part of the formula. So anyway, play around with the formulas and diagrams. Ideally, what happens is when you are solving homework problems, you'll look at both, right? You'll look at the formulas, but then you'll also be doing ray diagrams. So do some combination of both. Do the diagrams, do the formulas, work back and forth. Make sure that both the diagrams and the formulas are telling you the same thing. That's kind of the goal. That's the set of skills that you want to develop here. And we've got a lot of examples that we'll be looking at. We'll get to some in this lecture, and then in the next hour after this, we'll look some more. Okay, so let's start looking at some of these examples that we've got here. So here is an example. It's an image in a concave mirror. So remember, concave says it's going to be a converging mirror. And what it says is, I don't know why they picked a diamond ring, but they picked a 1.50 centimeter object, let's say, is 20 centimeters from a mirror, and the mirror has a radius of curvature of 30 centimeters. So they want to find out where is the image going to be, and how much magnification will we have. So it's a pretty standard kind of problem. So here we go. It's a converging mirror, and what we're told is that the object has a height of 1.5 centimeters. DO is 20 centimeters. The object is placed 20 centimeters from the mirror. And then the radius of curvature is 30. Now what we found was that the focal length is going to be 1/2 whatever the radius of curvature is. So if I got a radius of curvature of 30 centimeters, that's going to give me a focal length of 15 centimeters. All right, so let's see. I'm going to bring out that formula that we had looked at earlier and say, let me flip it around, because it turns out they told us the focal length, or we figured out the focal length, and the object distance. And what we can do is solve then for where the heck is this image going to be located. So I put all the numbers in and solved this very carefully. I ended up with an image location that is positive, and it's 60 centimeters. Now we'll see what this looks. Oh, our diagram is down here, I guess. So let's jump ahead of the diagram here. So it's kind of the same setup that we saw before. Now notice that on this diagram, I have not drawn the mirror as curved. And actually this, I'm going to say, is the correct way to draw your ray diagrams. If you try and represent the curvature of the mirror, your diagrams will be off. All the formulas that we're working with are derived in what we call the limit of the small angle approximation. And so to get everything to match up just right on the ray diagrams, actually just draw the mirrors as if they're plane mirrors. Don't show any curvature. So I got out my ruler and I carefully scaled this. I've got this reference dashed line going down through the middle. I put my object distance, I measured out, I scaled this. So here's the focal point. Here is where the object is located. There is the object height. Here is my DO. I put all that stuff in. And then I did those two lines that we talked about. Talked about a path coming in parallel. And then since it's a converging mirror, the return light goes through the focal point. Okay, path number one. Path number two is going through the focal point on the way in, and then coming out parallel on the way out. And then you just follow those lines out, see where they lead to, and wherever they intersect, we're saying that's where the image is going to be located. Now I only did two lines. I didn't do the third one. I guess I should have, to double check this and make sure that everything is working. But in any case, my diagram ended up looking like this. Here's HI, here's DI. And I think it worked because mathematically we came up with 60 centimeters here. And when these things intersected and I put my ruler back up to see where my image was located, I got something very close to 60 centimeters on the diagram. So again, work back and forth. Make sure that the mathematics, the numbers you're coming up with, match what you're seeing in the diagram. It's easy to make an error here or there, and if you are careful with the diagrams and the math, you'll be able to catch mistakes that come up, and you'll be able to get those corrected. So the distance here is 60 centimeters. Now I'm plugging this into my magnification formula, and my magnification formula is predicting that I'm going to get a magnification of -3. And so, yeah, that's what it looks like, right? The negative sign is telling me there's an inversion. I can see there's an inversion. And the HI is about 3 times what HO is. So it worked out just fine. Now, in this problem, they did give us a value for HO. They actually said it's 1.50 centimeters. So that's going to allow me to go in and actually use the magnification and say that the height of the image is going to be -4.5. Now, in this case, I've got a real object and I have a real image, which means if I put a screen right there, I could actually get an image showing up on a screen of whatever the object was. I guess it was a diamond ring or something like that. You could actually see an image of that showing up. Okay, so that's kind of like what these examples look like. So in this example, what they're really asking us about is what would happen if we took the object, which is currently located here, and we moved it to where the image is located. What would happen if we took the object and put it at the image location? Well, if we go back and look at these formulas that we have derived for this, notice that the formulas are symmetric. And by symmetric, what I mean is the object distance and the image distances are interchangeable. And what that's telling us physically is that the way light works, if light can follow the paths in the direction that our arrows are in this diagram, we can certainly reverse the arrows. So the arrows can always be reversed. And so if the arrows are going to get reversed, then I could have the object here. And if the object starts out from here, and we've got the very same focal length here, it's going to show up as an image at this location. So whenever I've solved a problem with an object and image, I can always reverse the object and image and say that's another solution That's another example of something that would work if we switch those numbers around. And that's what example 5 is getting at. All right, here is the example that I was starting. Yes, so what we've got here is a real object. But notice what's happened this time. Instead of having the object out here, past the focal point, we've actually brought the object inside the focal distance. What's going to happen if we take an object and we get really close to the mirror and actually past the focal length? What happens is the mirror is not converging enough to create a real image. And so what will happen is we'll end up with a virtual image. Let's see how that works. If we use the same paths that we used before. So let's say that I've got a light path array that comes out parallel, strikes the mirror, and then comes back through the focal point. So path 1 looks kind of the same. So far, so good. But when I try to create path 2 before went through the focal point. Well, I'm already past the focal point. I don't see how path 2 is going to go through it. Instead, what we're going to do is we're going to get path 2 so that it aligns with the focal point, but it's not actually passing through the focal point on the way towards the mirror. But it's still aligned with the focal point. That's good enough. If we align this path with the focal point, see those dashed lines, the light doesn't really follow that. It starts here, maintains that same orientation, and then it comes back parallel. But notice the problem I've got now is that path 1 and path 2 are not going to intersect on this side. It's just not going to happen. So I'm not going to get an image on this side, on the real side of the mirror. Now the person over here is saying, yeah, but I can see an image. And the reason for that is these two paths are oriented in a way where they're both oriented away from a point over here. Now, we've seen this before. We saw this with the bathroom mirror, the flat mirror. This is a virtual image. So the light coming off the mirror is not converging to a point. Instead, it's diverging, and that means we have to look back behind the mirror to see where that light appears to be diverging from. And so the image is back over on this side of the diagram. Now, this is what the ray diagram looks like. If we ran the equations for this, how would that appear? If we're doing the math on this problem, what would happen is the focal length would still be positive, because it's a positively curved mirror, it's a converging mirror. The object distance would still be positive, but when we solve for the image distance, we would find out the image distance is coming out to be negative. So watch for that. The signs will take care of themselves. If I get all the signs going into my formulas correct, if I get the plus and minus signs correct on the way in, and if I carry out the math correctly, then the solutions will tell me what's going on. So if we had set this up with a bunch of numbers, we would find that the image distance is positive. Now, what would we find out for the image height? Well, there's no inversion taking place. It turns out that the image orientation matches the object orientation. So HO and HI are both positive. Or they could both be negative, but it's easier just to say they're both positive. So that's how the math works, and this is how the diagrams work for those situations. And here is an example using that. So here are the different paths that we have going on. Here are some numbers. Let me go ahead and jump ahead just to the solution for this. You can go back, and the slides are always going to be available, so you can always go to Canvas and take a look at the slides. So what they've done in this problem, we've got an object height of 1 centimeter, we've got an object distance of 10 centimeters. It's the same radius of curve, it's the same mirror, 30 centimeter radius of curvature, and that says we still have the focal length of 15 centimeters. But now the object has moved inside. And so when we solve for the image distance, as we were talking about, now what I'm getting is I'm getting minus 30. There's a minus sign that comes out of the formula, and that minus sign is telling me that the image is located over here on the minus side of the mirror. And that's what we saw in our RAID diagram. I've drawn the RAID diagram here. Everything agrees. The diagram agrees with the mathematics. And then if I go in and I solve for the magnification in this case, I can get by using the minus di over do. Now, the do is positive, the di is negative, but there's a minus sign that's part of that formula that will flip the sign back to being positive overall. And I'm ending up now with a magnification of 3. And when I plug that into my formula for the image height, I'm getting 3 centimeters. So again, it's a concave mirror. Concave mirrors are converging. And this is what it looks like once we move that object inside the focal plane. Okay, so that's probably a good place to stop and take a break. So let's do that. I'm going to go ahead and take a break right there. We'll come back and we'll look at a bunch of other examples.